Let me first of all see my people. Share screen. Let me see the faces of all the people who are here.
Good morning, sir. Good night, sir. Good evening, sir.
Good night, sir.
Good morning, good morning.
Sir, is it 10 for you?
Pardon?
Is it 10 o'clock for you?
Yes, it is 10.
Okay.
And
Good evening, sir.
good evening. It is difficult for me to be teaching at 10, not because it is late. I only go to bed between 11 and 12. It is because when I talk, my wife can hear me, and so it keeps her up. But I send her away to my daughter's house, so I am alone. So that's okay
You are
now.
free to teach now.
Yes, I can teach. You see, I talk loud, and so it is inconvenient for someone who is in the house, and so that's good. Arjun, Siddhant, Karnam. Let me see your faces, guys. Today, there is Arjun. We did extended Euclidean algorithm. EEA is a backtracking after you get Euclidean algorithm. Backtracking so you can get the Bezout's identity. Now I will shrink the screen a tiny bit.
The homework was very interesting, sir.
Pardon?
The homework was very interesting, sir.
Yes.
A lot of time to solve.
Homework.
Yeah, because I kept on making mistakes on the last one.
Actually, I made a mistake. I'm the one who made the mistake. I had a mistake I made in the general solution of the linear Diophantine equation. I have sent Sai the revised file because there was a typo. I fixed it, and she will be sending you the revised one. You see, I'll come to that. Bezout's identity. Suppose you are given an A, B, and the GCD of AB is B. The Bezout's identity is there exists some X and some Y. In fact, a unique X and a unique Y. So you can write the greatest common divisor like this. That's the Bezout's identity. The extended Euclidean algorithm is the backtracking. So you can go back and step by step obtain this GCD in this form. That is the extended Euclidean algorithm. Now, I sent you already notes that the Euclidean algorithm ends after a few steps. Agreed?
Yes, sir.
Euclidean algorithm ends after a few steps. Now, because if you start with A and B, A equals, and let's assume B is bigger than 0, BQ plus R1, where R1 is greater than or equal to 0, but less than B. Let us say, if it is greater than 0, if it is 0, we are done, isn't it? If it is greater than 0, what do we do? What's the next step?
Then P is equal to R cube, R1 cube plus R2.
So we will call that, we will call this one Q1 and this one Q2, and this becomes R2. Now R2 has to be less than R1.
I don't really care what Q is actually.
What do you say?
We don't really care what Q is actually.
I don't say that again.
Sir, I don't think we care about what Q is.
Yeah, we don't. Absolutely right. We don't care about Q. But the reason I see, if I don't put a 2 there,
Then
and I
it will
put
be
a
an error.
1 there, they may be, some people may confuse that they are the same.
Yeah,
So it doesn't hurt putting there. That's a good comment.
it is better to put
What's
it.
the next step?
Then R1 is equal to R2Q3
R1
plus
equals
R3
R2Q3 plus
plus R3.
R3, where R3 is less than R2, and so on. Isn't that right?
Yes.
So what we are getting is,
It's like a loop where if the reminder becomes 0, then the loop ends.
so this must end because B is bigger than R1 is bigger than R2, and so on. Because B is a positive integer, there are only at most B minus 1 integers between 0 and B, isn't it? And therefore it must end.
Means including 0, no, between, sorry. Yeah.
Including 0, right?
No, sorry, I thought you said from.
Including 0, we have only B minus 1.
Yes, sir.
B minus 1 there. So there are B minus 1 steps in this algorithm. So that shows that the Euclidean algorithm after a while ends. I don't know this. There is a beautiful theorem. It says that the number of steps, I don't remember this, guys. Check the internet. The number of steps in the Euclidean algorithm does not exceed 5 times the number of digits in the larger of A and B. Haha, funny. Suppose A is 23 and B is 3,751. What does this say? What is the maximum, that number of steps here?
3,751 times 5.
It will be the number of digits in the larger one is 4. 4 times 5. There will be at most 20 steps in this Euclidean algorithm. Isn't that beautiful?
Yes, sir.
Well, we know there will be at most B steps, at most B minus 1 steps, but this one makes it a little bit even more precise.
But how do you know? How do you know this?
There is a proof of that. How do you know? Proof. Okay, we won't do that here, but if you type all that stuff in on the computer, you will be able to see the author of that, and the proof is supposed to be beautiful. Okay, and we will go on. Now, so that is that. I have another proof of that in your handout. Then we did the linear Diophantine equation, ax plus by equals c. Karnam, go ahead, sir.
Yes, sir. I wanted to say that the theorem which you said on the previous slide, it is called Lane's theorem.
Lame's that. Thank you. Lame. This is how you write his name. Lame's theorem. And you may want to read the proof. It is beautiful proof. Okay. This is called, what do you call this type of equation?
A linear diaphragm.
Diaphragm one.
It is a
Linear
linear
diaphragm.
equation.
Huh.
But this was investigated by the Greek Diophantus. And they are called Diophantine equations. And we proved that ax plus by plus c has solutions. It's already in the notes, guys. If and only if what? D divides C,
Divide C.
where
Where D is the GCD of A.
GCD of A and B.
we did that. And,
Yes.
and the beauty is, if it has a solution, suppose x naught, y naught is the solution.
Then there are infinite solutions for that equation.
Then that means ax naught plus by naught equals c. But then look what happens. Suppose you add t a b over something. What is it? And subtract t a b over d. The value of c is not changed, is it?
No.
But by doing that, look what I have done. I can combine these two and get a times x naught plus t b over d plus b times y naught minus t what? A over d equal
A
c
over
still.
Sir, sorry to
Yes,
interrupt you, but we can't see what you're writing on the. We can't see what you're writing below. Like
Okay.
ah, thank you. Let me see how I can raise it.
We can see it, sir.
Then
Sir,
you can
I will.
actually just press the Alt key and the meeting controls will be.
Okay, can you see this line, everybody?
Yes.
This
Yes.
line.
Yes.
Yes,
Yes,
sir.
sir.
Yes, sir.
That's so below that is the problem, isn't it?
No.
No,
You
sir,
can
we
see
can
stuff
see it.
below
We
that
can
as
see the
well.
whole thing, sir.
Yes,
So
sir.
you
Below
can
that,
all
sir.
see.
We just
Can you see
I
this
can see
line?
the whole thing.
Yes, sir.
Yeah.
yes, sir.
Then what is wrong with this crazy guy, Johan?
Sir, it was not
That
Johan.
was not Johan, that was Kirtan.
Johan, they are all saying they can see it.
Sir, I can see it. I really can see it.
Okay. So-
Kirtan said that.
If you can all see
No,
it,
I said
look at
that.
this. Look at
Sir, I
this.
said that.
Look at this now. So if it has a solution, t, what is t? T is any integer. So if x naught is a solution, any integer times b over d is another solution. And the value of y that goes with it. Now remember, these are linked. So we can say that x naught plus tb over d, y naught minus ta over d is the solution set for this equation. Beautiful. How many solutions are there?
Infinite.
An infinite number. Either it has no solution or tons of solutions.
Both extremes.
Right. Wonderful, wonderful, wonderful. Mind you, you might think that, well, I could have combined this and this and this and this. Couldn't I have? Then it would be like x naught minus TB over D, y naught plus TA over D. What? I say this solution set is the same as this, because T comes from the integers. Agreed? If this is 3, this is minus 3. So if you take T equals minus 3, this will become positive. If you take minus 3, this becomes negative, this becomes positive. So it is sufficient to take one of these. So I will go on to the next. This page is getting crowded. So we are done with that topic. Let us point out something. Continued fractions. Have you ever seen such a thing?
Yes, I think I have, sir.
No, sir.
Continued fraction. What is the continued fraction?
Sir,
of the-
I know what a continued fraction is.
Suppose I write 1 over 1 plus 1 over 1 plus 1 over.
I have seen this, sir.
So have I, sir.
This is called a continued fraction. I think the value of this is 1 plus square root of 5 over 2. I'm not sure. Okay. The golden ratio. Can someone check golden ratio and continued fractions on your computer?
Yes,
Does it look like this?
I'll check it.
Golden ratio is supposed to have, well, what is square root of 5 equal to?
2 point something.
1 plus what? 2 point?
2 point something. I don't remember what exactly it was.
Anyway, this is something like 1.6.
The golden ratio.
Sir, I
And
found it.
the golden ratio has the most beautiful continued fraction representation. I can't remember it. It's something along this line. It's supposed to be the
Okay, sir.
most beautiful.
Okay, sir, I got the golden ratio.
What
Yes,
is the
sir.
golden ratio continued fraction? What does it say? Is
So
it
it's
this one?
the same, the one which you wrote.
One person say it who saw it.
It's correct. I mean, the one which you
Yes,
wrote.
sir, it's correct. 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over, yeah.
Whoa, I am proud that I could remember it. This is also represented like 1, 1, 1, 1, 1, 1. They say real numbers, like real numbers that are not complex numbers, can be represented either as a decimal like we do 1.6134755, or as a continued fraction. Continued fraction representation has many advantages that this doesn't. For one, this is only in base 10, isn't it? In base 5, it won't look like this, would it?
No, sir.
So a decimal representation, deci has to do with 10. Duodecimal would be base 12. That will look different. So the representation as decimals is different based on the base you use. Of course, the general public only just uses, including us, just the base 10. And why use something else when you don't need to?
Actually, it's proved that the most ideal base to use is base 3. Actually, it's base E, but even
Yes,
round, you get
they
base.
say the ideal base is 12.
No, they say the ideal base is base E.
Base E?
E, but then they round it and they get base 2 and base 3.
E, I love the number E. A research paper I am just finishing I make heavy use of E. E is a nice number. It is 1 plus 1 over n to the power n. Limit n goes to infinity. Wow, that is Euler's discovery. And that is 2.7 something. Anyway, let us get back to, we are doing Euclidean algorithm. Continued fractions. Let us see.
Sir, can you
Suppose
tell the proof of
I have a doubt.
say that again. Who was
Sir,
talking? Go ahead.
I don't understand why you said that 12 was the ideal base.
Why 12 is the ideal base?
Yeah.
Well, it has to do with 12 having a lot of 12 has this diagram 4, 6, 2, 3.
E and more.
Okay, and they are both divisible by 1. It has a lot of divisives. I think it has to do with that.
Okay. Sir.
But I cannot answer you right now. I'm going to think of. I'm not going to think about it. You know why? I usually spend my time on deeper questions. So I'm not going to think about it. I will just read it in the internet. It is there.
Yeah.
Why base 12? What's the advantage or something? Google it. It is right there. Good question.
Yes, sir.
Good question.
Sir, I had a question.
Yes.
So can you tell the proof of this continued fraction? Like how did you get the answer? Because it's
Continue.
so simple.
Yeah, wait a minute. Continued fraction. We are continuing the continued fraction.
Okay.
We are not done with it. I didn't start it because it was just fun. It has something to do with the Euclidean algorithm. If
Ooh.
you give me a b bigger than 0 and an a that is an integer, then I can express a as bq plus r, where r is less than b, bigger than or equal to 0. Agreed?
Yes.
Yes.
Then I can write a over b equals what? Q plus what? R over Q plus R over B. I will call this R1. And that is the same as Q plus 1 over R1, 1 over R1, 1
So
over.
aren't you dividing B from both sides? Won't you get A by B is equal to Q plus R 1?
Is this wrong?
No, sir. If you take A equals BQ plus R1, and then you
Yes.
divide B, and then you
Then I am dividing.
you're
A-
dividing B from both sides. When you divide B
Yeah,
from both
I am
sides,
dividing on both sides and I get this. Am I right?
no, I think you get A by B equals Q plus R1, right?
Q plus R1 over B. We are dividing everything by B.
Everything by B, okay.
Of course, if you divide A over B, we have to divide each one of these by B. Okay?
Okay.
Now, is this correct?
Uh,
Yes, sir.
Now, watch this. B equals what? R1 Q2. Call this RQ1.
Yeah.
I
didn't get it.
Oh no, call this Q0, Q1. That is still Q0. Oh, okay. According to a theorem we know, we can now, okay, this is R1. We can now apply division theorem to this pair. Agreed?
Yes.
And we get B equals R1 Q1 plus R2. Therefore, B over R1 equals what?
Okay.
Q1 plus R2
by
over R1. That means that this becomes Q plus 1 over substitute. Q1 plus R2 over R1. Get it?
No, not
B
really.
over R1 is this. Now, we know R2 is less than R1. So what is the next step after this? R1 equals R2 times Q2 plus R3. Am I right?
Yes, sir.
Therefore, R1 over R2 is R1 over R2 is
R1
Q2
Q2
plus
plus R3 by
R3
R2.
over R2. So this becomes Q plus, just change color, Q plus 1 over Q1 plus R2 over R1 is what? 1 over Q2 plus R3 over R2. Get it?
Continued fraction, sir.
Did I make a mistake?
No, sir. It's a continued fraction.
Sir,
Say that
I
again.
couldn't understand from the purple part, sir, where you have it.
Okay, let's go back here. Continued fraction can be obtained using the Euclidean algorithm. Start with two numbers, one of them is bigger than 0. Apply the division algorithm. So this is good. Then you divide both sides by B, you get this.
Yes, sir.
You divide A divided by B is B cancels, you get Q0 plus R1 over B. Oh, this one is Q0. Doesn't matter. Okay, Q0. So this can be written as 1 over B over R1.
Yes, sir.
The reason is we are trying to bring it in the way a continued fraction looks like. And then you see this here. We can apply
Yes,
division theorem to this. We get this here.
Oh,
Okay?
okay.
And
Okay, sir.
then we divide B with R1, we get this. We take that B over R1 and substitute this here. Okay? And that's how you get this. So
Okay.
this goes here. This is clear.
Yes, sir.
And it will be in the notes I sent you. And you repeat this. So you get like this. Hey, guys, guess what? This continued fraction is written like Q0, Q1, Q2, etc. Finally, the greatest common divisor. Okay? Beautiful. Don't you see the beauty in it? But there is more. But there is more. And that's what I wanted to conclude with. You see, Euclidean algorithm terminates after a while. Agreed?
Yes, sir.
If Euclidean algorithm terminates, there are only at most b minus 1 of these. Is that clear?
Yes.
Oh,
That means that any fraction that is not repeating has a finite continued fraction representation. Is that clear?
Yes, sir.
There are only up to b, no more than b minus 1 numbers here. Maybe it is b, I don't know, including b. I don't think it is b, it's b minus. So a fraction like n over m has a representation. Unless it is a repeating decimal, wait a minute. Wait. Every rational number, aha! Every rational number, beautiful. Every rational number is ratio. Every rational number has a finite continued fraction representation. Wow, this is wonderful. If it is decimal, 1/3 is not a 0.3 repeat, isn't it?
Yes.
It goes forever. But in continued fraction, it doesn't. It's done right there. Sitting right there. So that's the beauty. So you see, Euclidean algorithm allows to represent fraction, rat number as continued fraction. Question actually?
Sir, when you first mentioned the Euclidean algorithm, you said it's in some famous book. What book is that?
Famous what?
A book.
Famous book. I talked about the other day.
The elements book or something.
Oh, that one. Somebody tell us. Somebody already bought it. The most famous book in the world.
So it's elements of Euclid.
The elements of Euclid.
Okay.
Okay.
Okay, sir.
Let's go on. We will end this topic before. What time is it? Okay.
It's
Euclid's lemma. What is a lemma? A lemma is a result. You prove, so you can use it in proving another theorem. Okay?
Sir, like lemma and reminders.
Say again.
Like the lemma and reminders.
Lemma on the?
Reminders.
Lemma on the remainders. Let me see.
Yes. Sir, the sum product of any two natural numbers has the same remainder when divided by k as the sum product of their remainders.
I see. Right. Such results. So you have a lemma, you have proposition, you have a theorem, you have a corollary. These are the things, these are the statements that mathematicians, when they prove, they take this form. Euclid's lemma says the following. If P is a prime and P divides AB, that will mean either P divides A or P divides B. Famous lemma. Very useful. Okay. Suppose, and the proof is so nice. So, suppose P divides AB. Suppose if P doesn't divide A, then what is the GCD of A and P?
D.
If P doesn't divide A, the greatest common divisor of them is 1, isn't it?
Really?
If two numbers have no common divisors, well, every number has 1 as a common divisor. Is that true?
Yeah.
Yes.
Every pair of numbers has 1, is divided by 1, each of them.
Yeah.
So if P doesn't divide A, well, at the
But how do you
greatest
know?
common,
How do you know if P doesn't divide A and the GCD of A and B is 1? How do you know that?
say that again.
Sir, how do you know that if P doesn't divide A, then the GCD of A and B is 1?
Wait a minute.
P
P
is prime.
divides AB. Then one of two things can happen. Either P divides A or P doesn't divide A. Follow?
Yes, sir.
If P doesn't divide A, nothing divides P except 1, isn't it?
But
Only
that's
number
why,
dividing P is 1. And
Sorry,
1 also divides A. And 1 is the greatest common divisor of A and P. Do you agree, OV?
sir, but so you said suppose P divides AB. So then, accordingly, you're writing the second sentence. But then, how can it be true?
Well, suppose A divides B. Okay, good. That doesn't mean P divides A. Let me give you an example.
But sir, okay, imagine if P is 6 and A is 8. The P doesn't divide A. Then GCD of A and P is supposed to be 1, but it's not, it's 2.
For example, 7 divides what? 7 divides
14, sir.
7 divides 14, right? 7 divides 2 times 7.
Yes.
7 divides AB. And if 7 doesn't divide 2, it must divide the other number, which in this case is 7. Okay?
Yes, sir.
That's what it is.
Sir, GCD is 7.
Oh, no. Come back. All right, now
Aren't we trying to prove that?
we are trying to prove that if P doesn't divide A, it will divide B. Okay?
Okay.
Okay.
If P
Yeah, I got
divides A, we are done, right?
Yes.
Remember, we are trying to prove this. If P doesn't divide A, we will show that P has to
Sir,
divide
I have a
B.
little doubt.
Yes.
Sir, P is prime, right?
Yeah.
Okay.
So even I have
Sir,
a
in the
Sir,
GCD,
P
Yeah,
it need
oh,
not.
I
So P need
forgot.
not be prime.
I forgot. Thank you, Arjun. P is prime.
Sir, but P need not be prime because if P is 8 and A is 6, then
Oh, if P is not prime,
Okay,
you can extend this to sufficiently modify this and get a result. Okay, but Euclid's lemma is when P is a prime and P divides the product of two numbers, it should divide one or the other, or
I have
even
another
both.
example that P need not be prime. 8 and 9, for example, sir.
Yeah, it may
9 is
be
not
true.
prime.
It may be true. Give me an example. 8.
8 and 9.
Okay, what about that? 8 and 9 are composite numbers. But we are talking about a number like 11 dividing a number like, I don't know, 1507.
Okay, so here we're only taking, here we're assuming that P is prime. There are other examples where P is not prime.
Yeah, we are assuming that P is,
Only when P is prime.
we are assuming that P is
Okay,
prime.
thank you.
This result can be redone with P not prime, but it will be a different conclusion. So now tell me, do you agree with this? That if P doesn't divide A, do you agree with this statement?
Yes, sir.
P doesn't divide A, but
GCD of A and P, right?
yeah, it will be 1.
Okay.
Why?
Yeah.
Why? First of all, is 1 a common divisor of A and P?
Yes.
1 divides any number, so it is a common divisor. Is there a bigger number that divides P? The only bigger number is P itself. But P doesn't divide A, so P is not a common divisor. Follow? So
Yes,
1 is the greatest common divisor. Is everybody convinced about this one?
Yes, sir.
Yes, sir.
Let me have a show of hands. If you are happy with this conclusion, 2 people. We need everyone on board on this one. The greatest common divisor of A and P is 1 if P doesn't divide A. Because the greatest common, the biggest number that can divide this is P. But P doesn't divide A. So P is not a common divisor. No other number divides P because it is prime. 1 is the one. Thank you. Everybody can put the hand down. Now, oh, wait a minute. Wait a minute. Bezout's identity. What is it? GCD of AB is some A times some X plus B times some Y. Agreed?
Yes, sir. Agreed.
So, what is the GCD here?
1.
So, 1 equals some AX plus B times some Y. Is that true?
True.
Do you all agree with this?
Yes, sir.
Yes. Karthik,
Yes, sir.
Kirtan. I like that name, Kirtan.
Thanks, sir.
Siddhant. Arjun. Everybody happy with this?
Yes.
Yes.
Yes, sir.
Multiply both sides by B. BAX plus what?
Multiply what? Both sides by what, sir?
B.
I am
Sir,
hold
B
on.
squared Y.
Which one do I? Yeah, but why am I getting the P squared? Let me check something here. Why am I getting a P squared? Okay. B.
You get BX plus B squared Y, right?
B multiply AX Oh, look at the mistake I made. What is B here?
B as P.
P. No wonder you guys had a problem with that. Agreed?
Yes.
Oh,
A,
Yes, sir.
A and
oh, it's A and
P.
P, not B. Okay.
So
Wait,
this is
I knew that P was P. I knew that.
BPY. Okay.
BPY. Okay? All right. Now,
Max plus BP.
wait a minute. Now, what happened? P divides AB. P divides this. So you can, this implies P divides B. Are you convinced?
Yes.
P divides AB means AB equals some Q times P, isn't it? P divides AB means AB is some Q times P. So if you like, you can write this as B equals Q times P times X plus B times P times Y equals P times QX plus what? QX plus what?
BY.
BY.
Aha! B is a product of P and something. Therefore, P divides B.
Yes, sir.
Proof is done.
Yeah.
So one question.
Yes.
Sir, why did you cancel that B, like Bezout's identity after that first line? GCD of A and P is equal to AX plus Y.
Oh, here I should put it back. PY. You see, GCD of A and P is 1, not A and B. Follow?
Yes, sir. Thank you.
Therefore, in Bezout's identity applied to this gives us 1 equals AX plus what? PY. Agreed?
Yes.
Yes, sir.
And so I rewrite it. 1 equals AX plus BY, so B equals this and there. Do you understand this proof, Johan?
Yes, sir.
Kirti,
Yes, sir, I got the proof.
Yes, sir.
Ovi,
Yes, sir.
Atri.
Yes, sir.
All right. We can go on. I think I have spent enough time on the Euclidean algorithm, which is actually a tool, another tool of proof. Now we go to the last method of proof I want to discuss.
Induction?
This is the name. Pardon?
Is it induction?
Yes. Principle of mathematical induction. And that has to do with something. Yes. There was a man by name Piano. Okay, not piano. No, his name was Guitar. No, it was Piano. Giuseppe Piano. He's dead over 100 years now. 120. But he still
120
lives.
to get converted.
One day, once I was giving a speech to a bunch of students like you. I think at that time there was about 1,200 students like you. Some place I was giving a speech and I told them, the only thing I know not to die is to discover a theorem or propound an idea. And you will live on in the memory of people for a while. Peano came up with in 1889 or approximately there, axioms for natural numbers. What is a natural number?
Natural number is any number that is not positive.
It is the numbers 1, 2, 3, etc. Okay. When you are more advanced, you will take a course called the set theory. Oh, that's what I am teaching the Brahmagupta group. And there I showed them how to construct the natural numbers. What is the number 1?
Number 1 is
Well,
0 plus 1.
the very young students like you and the public think they know the number 1, but they don't really, okay? And you will understand next year if you are taking this course. I'm not sure, not this course, the set theory course. I'm not sure. You might be the last group of students I might be teaching, guys. And I probably will, I should publish this little book on set theory and all this stuff. So I don't have to lecture. I'm too busy with the research right now. Because, you know, I am old. I need to spend all my time on this too.
You know, most of the time, old people don't do research.
Pardon?
No, you're probably one of the few people, old people who do research. But I don't know
Yes,
any.
yes, I stay fit, very fit, by running and not eating too much, not eating junk, and things like that, you know. Anyway, the point is, when you take set theory, you will know what this natural numbers is. This guy Peano in 1889 wrote down some axioms. Amazing it was. He said,
What's
What
an
is
axiom,
this?
sir?
What are the axioms? He said, there is an object called 1 contained in the natural numbers. Do you know the symbol?
Yes, sir.
Okay, this means there is an object. Let us call the natural numbers n. Then he said, there is an object called 1 which is in it. That's the first axiom. The second axiom is, if there is an object n in this big N, then a successor of n is in n. I will explain that.
Sir, can you explain the first and second?
Oh, sure, I will.
I got
will-
the second one, sir.
I will be explaining it.
The first one doesn't need any proof. One
Okay.
is possible.
Usually they write, if n contained in n implies n plus 1 contained in n. That way, there is no gap. Suppose this is, if n is contained in n, n plus 2 is contained in n, what set will you get? You get 1, you get, what's the next one you will get?
3.
3.
Five.
Why?
9.
It will be missing a whole bunch. Follow? So usually when this is presented, mathematicians will write n plus 1. But you don't have to. It is n plus 1 is sigma n equals n plus 1 is forced on us. You will. I don't
So
know if
what
I
is
will do.
sigma?
This is called the successor. Successor of n. Successor of n. Okay? That is a term in his axiom system. Sigma. So if there is an object called n in it, it has a successor in it. What is the successor? He's not saying it is n plus 1. He's not saying that. What is sigma n is described by the axioms that follow for n and m contained in n. If sigma n equals sigma m, then n equals m.
But sir, I had a question.
Yes,
Sir, immediate successor or any successor after that?
say that again. Say that again.
The immediate successor of n and m or any successor of m and n?
Is the immediate successor. Okay.
Then yes.
But if
Immediate.
sir, but if it's the immediate successor,
Now
then
you
we do-
see,
then we should do n plus 1, no, sir?
yeah, well, we should do n plus 1, but n plus 1 will come out. Okay. This the reason why the people.
Sir, I didn't understand how n plus 1 will come out. Again, can you explain?
We'll see. So if it was n plus 1, n plus 1 equals m plus 1 implies n equals m. Agreed?
Yes, sir.
Okay. In fact,
So
if it
what
was
is-
anything, if this is n plus alpha, and this is m plus alpha, then again n equals m. So this is not enough to show that alpha equals 1. Let us see further. All right.
So what is a sigma?
What is sigma? Sigma is a successor of n. You see, what is happening is he is thinking of n as a set. And he's trying to come up with the properties of the natural numbers using these description, these axioms. Let us see, continue here. Sigma n is not 1 for every n. What? That's a strange one. Sigma n is
Sir,
not,
that means n is greater than equal to 1.
sigma n
Yeah.
is not 1. That's all it says.
Okay.
There is no greater than or anything yet.
Okay.
This is a set. Sigma n is not 1. So this says that among other things, I will erase this. One is not the successor of any n. Does that
So what
say
is that? L?
one
Oh, okay.
is
Okay.
not the successor of this? Among other things, is saying that you cannot get one by sigma n. You cannot take an n and get one as its successor. Follow?
Yes, sir.
It is trying to say that one is the first thingy. It is not the successor of anything. Not done yet. And here comes probably the second most famous theorem in the world of mathematics. 5. Peano's fifth axiom says, let T be a subset of N. Do you understand what a subset means?
Yes, sir.
If you take A, B, C, a subset is, how many subsets this has? 8, right?
Yes.
Yes, sir.
And here is one subset. That is a subset. A subset has some of the elements of the original set. It could have all the elements, in which case it is the same. Suppose T is a subset of N, like let us take 20 numbers, such that, can you still see what I am writing?
Yes, sir.
Can I move this up? Let me see. Maybe I can. Can this? Is that better? Is it a
Yes, sir.
little bit higher on your screen?
Yes, sir.
Let T contained in be such that we will move away from this theory shortly, guys. Don't worry.
Okay, sir.
A, 1 contained in T, if this object is in that subset, and if whenever M is contained in T, then sigma M contained in T. Suppose you have a set with this kind of property, then T is the whole of N.
Makes sense.
This is called Peano's, this is the fifth of Peano's axioms. The principle of mathematical induction sits on this axiom. And I will show you how. And let me see. I think I will continue this in the next class. Oh, there is time. I still have 10 minutes. I am a happy man. I am a happy man. Now, 5. I will repeat it.
Wait, sir, you wrote
Sir, can you go
A.
back 1 second?
Yeah.
Sir,
I
can you
need
What
to
go
see the
back?
previous slide.
Or I will send you the notes.
Yes, sir. What is that AIET?
What is the what?
Yeah, in the fifth one, you have written AIET. Oh, I consist in T then.
1 contained in T. If
Oh,
M contained in T, then sigma M contained in T. The successor of M is contained in T. Okay. Now,
sir, I don't understand what this
what
thing
I
is
will do
trying to
is,
tell us.
for now, I know your difficulty here, don't worry. For now, assume, because I don't have time to prove it, that sigma N is N plus 1. Half your difficulties will melt right now. Okay? The successor of N is N plus 1. So you have 1 in this set. You have 1 in this set. Whenever N is in the set, N plus 1 is in the set. And if N plus 1 equals M plus 1, then N equals M. And 1 is the first element. And this. We will come
Sir,
back
I
to this.
don't get the fifth statement. I don't get the
Say that
fifth
again.
statement. Sir, I don't get the fifth statement.
You don't get which one?
The fifth one.
The first one?
The fifth axiom.
First axiom, this one,
The fifth,
the next
5.
one, 5.
5. Yeah.
Okay, the fifth axiom, you see, I wrote 5 here. I was going to explain it. I have some explaining to do. Okay, it says, let T be a subset. I'm going to rewrite it. Let T be a subset of N,
Okay, sir.
such that, you will become very familiar with this axiom. A, 1 is contained in that subset. B, if M is contained in the set, then N plus 1 is contained in the set. Think of sigma N as N plus 1. Then, if there is such a set, then T equals N. Now, let me do it another way.
Wait, sir. If n
Yes.
plus 1 is contained in the set, then n plus 2 is also contained in the set, then n plus 3 is also contained in the set.
Yes, that's
So that
right.
means t is then all the natural numbers there is.
That's
So t is
right.
n.
T is equal
Exactly.
to N, actually.
Yeah, but you see, when you are dealing with an infinite set, we cannot just say and then and so on, and we have to write it down in steps.
Yes, sir. But what is the point
Yes.
of making t? Because t is n, then what is the point of making t?
You see, this is really, I am unable to explain that here because you see, N is called an inductive set. That's a slightly long story, okay, to fully understand this. And N is an inductive set like this. You can get from one to the next it contains all the successors. That is called an inductive set. If one is in the set, and if all the successors are in the set, it is called an inductive set. Not only that, N is the smallest possible inductive set, and T is an inductive set in it. Because N is the smallest one, T has to be N. Follow?
So an inductive set is a set which has.
This is essentially saying that T is an inductive set, but N is the smallest inductive set. If N is the
T is
smallest,
equal to M, T is also the smallest inductive set because it is equal to M.
If N is the smallest inductive set, and if T is also an inductive set and it is contained in N, implies T equals N. Okay?
Okay, sir, but what exactly is an inductive set?
An inductive set looks like this.
Okay, sir, thank you.
Sir, I have a question.
Yes.
Sir, you have written if M belongs to T, then N plus
you are
1.
right.
Right.
Excellent. Typo. No, righto.
Lol.
That was
Right.
a right. That was a righto. Okay.
Or you can change it to Rarito.
Burrito.
Yeah,
A
Rarito.
burrito.
Popular pen drive.
Okay. Let us now, we will take this axiom and consider this. We will call it the fundamental theorem of mathematical induction. It is essentially this axiom you will see shortly. For each n contained in n, let Pn be a statement. You know, in about 50 years or in under 50 years, we don't have to write like this. All we have to do is think. and it will appear. Within 50 years, that will happen. And I think in about the same time, in over maybe in 100 years, you don't have to listen to a teacher. You can download all this directly into your brain.
Yeah, that would be really cool. I don't have to sit in a
Yeah,
class.
that will be sad.
So I'm pretty sure a few hundred years ago, people were carving things on stones and copper plates and
People
all.
will be able to acquire knowledge in such fantastic ways.
And so a few hundred years back, people were carving things into stones, and they'd be like, a few hundred years later, we only have to sketch it, and then the outline will magically appear. Rather than have
Absolutely. Absolutely. So for now, for me, I have to really work hard to write. Let P be a statement that is either true or false, but not both. Wait a minute. I don't even have to write this, but I wrote this anyway. You know why? The statements we use in mathematics are called declarative statements. They declare something. And declare it is like saying.
Sir, you told us in the first class.
Pardon?
Sir, you told us in the first class the types of sentences.
Declarative sentences declare something. They are either true or false, but not both. It is like saying Ganges is in America. Same way. So suppose you have a statement, but this time it depends on the integer n. Let t equals all those integers n contained in n that make Pn true. Well, then this will be a subset of n. Is that right? Don't you agree? All the integers, all those integers, for example, let us make a statement like a Pn. Suppose I said n squared plus 2n is a square. Suppose I said that. Then not all integers are in it, but some will be in it, right? I don't even know if I wrote down something fantastic. So those integers that make this true are the ones in this set T. And they will not be all of n. For example, is 1 here, 1 squared plus 2 is 1 squared? No. So 1 is not there. But there will be probably some n in it. All right. Now, if 1 is contained in n, 1 is contained in T, 2 for all n contained in n. Do you understand this notation?
Yes, sir.
N contained in T implies n plus 1 contained in T. Then what does Peano axiom say? Then T equals
N.
n. We are getting closer. This is the fundamental theorem of mathematical induction. Now, well, we can go a step further. We can say, instead of saying, let T be the set of natural numbers n such that the statement Pn is true, we could say the following. For each n contained in n, let Pn be a statement which is okay if 1 P1 is true, and 2, PK true implies PK plus 1 true, then PN true for all n. There is the principle of mathematical induction that the public knows. Peano axiom, fundamental theorem, and then the method of or principle of mathematical induction that the public uses. So, let's see, write it again.
Sir, can you go back to the previous slide for a minute? The one before. Yeah, this one. Just a minute. No. Where you wrote the fundamental principle axiom. No, sir, where you wrote if one.
Hold on, I'll be back.
Okay.
There. Fundamental, I see where I wrote fundamental. Right?
Yes, sir. Yes, sir. Thank you. Just a minute. I'll just copy it down.
You will get that in the notes anyways, guys.
Okay, sir. Thank you. You can.
Now let me write it again. Suppose, here is the mathematical induction. Suppose P1 is true, PK true implies PK plus 1 true, then PN true. Okay, let us see. Look at this thing. We'll do one example and be done with it. Let us take the integers 1 plus 2 plus 3. Every instructor does this. Supposed to be n times n plus 1 over 2.
Sir,
So here is my statement, Pn. I am making the statement that if you add the first n integers, you get this. That is my statement. So what do? You check, is P1 true?
Yes.
1 equals 1 times 1 plus 1 over 2.
Yes.
Correct.
yes, sir.
Now, if that is correct, assume this. PK true implies PK plus 1. What does that mean? PK true means 1 plus 2 plus 3 up to K equals, give it to me. Apply the formula.
K plus 1 by 2.
K into K plus 1 over 2.
So
You can
then
assume this. You can assume this to be true. Then you show that PK plus 1 has this form. If you can, then it will be true. The formula will be true. 1 plus 2 plus 3 plus up to K plus 1. Isn't that 1 plus 2 plus up to K plus K plus 1?
yes, sir.
Now,
We'll
isn't that
substitute the
K times
answer
K
from-
plus 1 over 2 plus K plus 1?
Yes, sir.
Yes, let us factor out K plus 1. K plus 1 times
K plus 2.
K over 2 plus 1. And isn't that K plus 1 times K plus 2 over 2?
Yes,
So
sir.
that is
Yes.
K plus 1 times K plus 2 over 2. That is like, hey, wait a minute, that seems to be true. If you change this to, if you change that to K plus 1, this will become K plus 1 This will become k plus 1. So it is k plus 1 times k plus 2 over 2. Whoa, wait a minute. So the formula holds. If it holds for k, it holds for k plus 1. Therefore, it is true for all n. Get it?
Yes, sir.
This is the principle of mathematical induction application. I said, this is a method of proof. Just like well-ordering principle is a method of proof. Now, I'll give you some homework with the notes, and then you will become familiar with it. Now, in the next class, we will spend a little bit time with this principle of mathematical induction. Then I think I will give you a. Is the next class the last one?
Yes, sir, I think so.
Yes, sir.
I'm going to
Yes,
give
sir,
you.
tomorrow is last class.
I will give you a test.
Ooh.
Oh, you are scared, are you? It is all that means you have to study the notes. Especially, I will be asking you a few things like what is. I can even tell you what is in the test. The laws of thought.
The laws of thought.
What is that?
It's the
Have
thing
you
we
heard of
learned
that
in the
before?
first class.
First class. What we
remember
learned in the
that.
first
Yeah,
class.
first class,
The
I
3 laws of
remember.
thought.
The law of identity, the law of
Law of
non-contradiction,
identity,
the law
law
of
of
excluded
non-contradiction,
middle.
and law of excluded middle.
Excluded
A
middle.
is equal to A and not A is false.
Frege
A
identity,
or not A is true.
Not
Frege
Frege.
identity,
Oh, I remember Frege, not P or
modus
Q.
ponens,
I don't remember that.
I remember mod opponents, but
and then I'll give you a simple statement. You prove it using counter positive.
Sir, what is counter positive? So it is if P implies Q, then not Q implies not P.
You read the notes. Direct proof, counter positive, inverse proof by contradiction of premise,
Reductio ad absurdum.
RAA, reductio. Okay. And I think
Then the
there will be
relations.
plus maybe another item. That's it. So that is fair.
Yeah.
Well, what kind of teacher is that? He is telling you what is in the test.
But
Yeah.
sir, you know what lessons are there for the test. You just prepare for them.
Yeah, that's blueprint.
Yeah. Wait, actually, all teachers do that, sir. They'll tell
The
you what
reason is,
lessons are in
guys,
the test, so you study them.
Especially you are supposed to know this and this all your life if you want to be a mathematician.
What about Frege identity?
Frege is good but we don't usually use it.
Okay, sir.
Frege is useful in physics, in some of these things, proving proof by contradiction and all those things. It might be useful, but you need this after a year. If somebody asked you what is proof by contradiction of premise, and you say, I don't know, it was a year ago I took the course. That's not how it is. This must become hardwired in your brain. That is why this course is very fundamental. Okie dokie, so that's what we will do. In the second, we will probably spend the 15 minutes on this one and 1 hour on this, so you have all the time. Is this fair?
Yes, sir. How many questions are there
Yes.
going to be?
I don't know. 1, 2, 3, 4, 5, 6, 7, 8, 9.
Okay. For how many marks?
How many marks? You tell me. 90?
9?
90 marks?
Each
No,
question
9,
is
right?
10 marks, sir.
10, right? It's 10.
See, it is not to make you pass or fail. It is for Sai to 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 know how you understood this
Yeah,
series
because
of
we do
lectures.
not have time to take an exam, really.
It is I mean, it is not like an exam like in school. Okay, this is about these concepts. See if you got something.
Like in schools, after a few months, they will always take a quiz, right?
Say that again.
In schools, after a few months, they'll always take a quiz, right? Like that.
I still didn't get you.
Sir, in schools, after a few months, they will always take a quiz on what you learned. So I guess this is like that.
After a few months, what will happen?
They'll take a quiz on what you learned.
Oh, they will take a quiz. Oh, this is like a quiz, isn't it?
Yeah.
Yeah, okay. Yeah, you should teach other people these things, your close buddies, because they don't have the opportunity to learn these things. Okay. You cannot teach these things in school to everyone because not everybody is interested in math.
Yeah.
Okay. Most people are not interested.
If there
Most
was
people are,
no general public, then we'd make great discoveries in math by now. Lots and lots of great discoveries.
most people are not. The reason is it happens at home. You see, you guys at your house, you were faced, your parents made you face a math problem when you were little, like
Yes.
when you were 1 or something.
Yes.
1 year old. 1 is a good
I don't
number.
remember.
I remember when they gave me 1 + 1 and then they told me it was 2. And then they gave me 2 and they said
They probably presented you with a math problem, gave you 2 balls, and then took it away, and then gave you maybe 2 other color, different color, who knows? And you became confident. Oh, that's that thing that you see. Then they probably presented you. I don't know. Something happened that you see. People are smart. Most people are very smart. It is that their smartness lies in other directions. Yours grew in this direction. Then you were presented with another problem or situation which you climbed there in understanding. Your parents did this to you. Okay? Your confidence rose. That is why you are here now. Okay? But if it went the other way, if you go this way, this is what happens to most people. And now they think they are bad in math. Okay? They are smart, but they were faced when they were little with situations that they couldn't do. Something unfair happened to them. So you should really thank your parents.
Sir, I don't get it. What did you say?
You were somehow, whether they consciously did it or not, you faced situations that you could figure out. Follow? When you figure out a situation and again you figure out the next one, your confidence increases. This is all about confidence.
So at a young age, they could give you difficult
It is
questions.
very important in mathematics and music, athletics. You have to get into it when you are little. See, the big discoveries are made before you are 40 years old. Not when you are 75 like I am. Forget it. So this is why you have to get in early. You have to get in before square root of 40.
What's this? That's before you're 6 years old. Around.
Sir.
So good for you. You are the good for you that you have this
Years old.
passion.
Sir, not square root of 40. Wait.
Square root of 40 is what? Well, it's only a little more
Sir,
than
square root of 200, not 40. So, sorry. Yeah, square root. No.
square root of
Square root of 400.
Yeah.
No. Square root of 40.
400. 40 is.
well,
36.
most discoveries are made before this.
Sir,
Right?
that is 40.
I think we
Age
have
of
more
40.
fun talking after the class than we have in the class.
Sir, the square root of 40 is less than 7. So we have already exceeded that age.
Oh yeah, you guys. Oh man. You guys are it. Okay?
Sir.
All you need is passion and grit.
So, what's
You know
great?
what grit means?
No, sir.
Determination.
Grit means you don't quit.
Yeah, determination.
I am one of those guys. That's why I still run marathon. Grit, grit.
Sir,
Great.
I googled you up and I saw you running the marathon.
Say
Yes.
that again.
I googled your name and then there was a photo of you running the marathon.
So did you really run a marathon when you were 72?
You can see my book on Amazon. Hey, Johan, you should tell your parents to buy
I
that
saw
book.
your book on Amazon, Against All Odds.
Yes. Did you?
Something about lotto.
Oh, I want to show you something. Hold on.
Still runs. Wow.
Kirtan is very wise.
I couldn't find it. It was about pi. I had pi on one of my books. That was beautiful. Where is my book? Sorry, guys. Okay,
Sir.
I'll show you another.
I have a
So
question.
that's it. We have purposely exceeded the time by,
Sir, I have a question.
yes.
Will you give us a discount on your book because we were your students?
Oh, I don't get a discount on my book. I don't sell it.
Why don't you talk to Amazon?
Okay.
I don't
good.
need to. You know, I mean, I write things and they sell it and whatever. You
So
know,
what? Okay.
But what about royalties? Don't you
I
get
was just joking.
Don't you get any royalties?
Yeah, you should get royalty, right?
I didn't get it.
When you publish a book, you get a bit of the money for
Oh yeah, yes.
right.
That is true. But
But
you don't do things. You need money, but mainly you pursue your passion. You know.
Yeah.
did you get the royalties?
Yes, royalty comes. Yes. Yes, but I spend it all on charity work.
Oh. Sir, how many books have you published?
Oh, I have published only 3, but there are 2 more on the way.
Oh.
Sir, what are your 3 books?
One of them is called Against
All Odds. Yeah,
Sin
Yeah.
and Danger. This is the one about running on the Indian roads, elephants and cows and everything. This was a while ago. But nowadays, there is no cows and all that because just cars, isn't it?
Yes, sir.
Number of years ago, that's one. This is the one on Amazon. Then I have Against All Odds.
Sir, your books seem to start with against.
Yeah, so I think I like it. This is called the Against series. The other one is called Against Epsilon Camp. No. Against
Sir, in the
gamblers.
chat, they're calling you Dr. T or Dr. Big Inspiration.
Against gamblers' ruin.
Wait, that is actually a book?
Yeah, this is not on Amazon yet.
Oh, okay.
This is these are all actually, you know, these are all education for the public, really. Okay,
Hmm.
I'm telling people,
Sir, how many papers have you published?
not many, only 6.
Oh, okay.
The reason is a mathematician by now should publish at least 150 papers. Okay,
Whoa.
but
150 books.
papers, researches. But what did I do? Instead, I founded 5 camps.
Wow.
Yeah.
Sir, what are the 5 camps?
I spend all my time.
And all of the people in the camps are going to put research papers. So that makes you buy now a lot more than a mathematician who didn't found camps. Because you founded the camps, a lot of people got the higher mathematical education. And so they're going to publish
Yes.
papers.
Well, I have happiness because I have thousands of students who went through the camps. Hopefully, they will continue with their math and so on. So I am basically happy.
So what about
So-
your patents? You have patents?
Pardon?
You have patents, right?
Yes, I have 2 US patents. I have a ton of trademarks. And so on. Has to do with education. One of them is very interesting. It is a device that you put in your mouth when you run. So even if your mouth is open, the virus and the pollens don't go into the mouth. So I think that is going to be useful soon because of this COVID.
Sir,
You
you
can also
designed
push it into the mouth of the very old people like me, sitting somewhere, sleeping with our mouth open, so the flies don't go in. Nice chatting with you guys.
Sir,
Did
but
I
I
see-
can't find any of the books on Google except Against Dining Danger.
Against All Dots, Din and Danger is only in India.
Okay.
Sir,
Against,
Sir,
against
I
all
Because I
found
odds,
cannot see any other ones on Google.
Against All Odds, it has a subtitle actually. It is called how
because there
to
are many of them.
how to play lotteries if you must. That is the subtitle. Look at the subtitle.
okay.
That's a nice subtitle. If
Yeah.
you must.
If you insist that you want to play, then I will show you how. You
Sir,
follow?
isn't that game theory? A little bit.
Yeah, it has it
It
is
is
mostly probabilities and so on.
Okay.
See, essentially it is saying, suppose you are saying you are on the 8th floor of a building and you come out of the balcony and say, I am going to jump. Okay? I'm going to kill myself. Well, I'm telling you then how to jump. You have decided to jump. So I will show you how to jump so that you'll be still alive. So that's what that is about. Okay, we had a good session. Our
Sir,
last class is last class
sir.
is tomorrow.
Yes, sir. Before you go, I'm going to send one link in the chat. Can you just see that link?
Chat link. 99 plus chats. This one?
The
The most
big
recent
one.
one.
The big one, sir.
It's the
That's a
Google
big one.
Images search.
Yes, sir.
So how do I click on it?
Yeah.
Yes, sir. Just click on it.
You are
Oh my
shown as
God.
a math path, factual and stuff. And
Where do you get all this stuff?
Sir, I just Googled your name.
I see.
There is a
Okay,
photo of you running the marathon.
So see you tomorrow, right? Sai,
Yes, sir. Yes.
tomorrow is the last class, right?
Yes,
Yes.
Sai, when is the closing ceremony? I am so busy. I have so many other.
Yeah, it's tomorrow evening. I'll send you the time and Zoom link
Not
details.
tomorrow, for you, it is right now. You are on Friday, so your
Yes.
Saturday evening, right?
Yes.
So
I'll
that
send
is
you
my-
the
Right.
I'll send you the timings and Zoom link over email.
Yes. So that's Saturday morning. Yeah.
Yeah.
Good. I play soccer in the afternoon. Good. Yeah. So that's okay.
Soccer.
Yeah. I'm a soccer player.
Wow, really?
Yes.
Sir,
So-
what other sports do you play other than running a
Yes.
marathon and playing soccer?
Just soccer.
Oh.
I am the oldest soccer player in this city where I live. Yeah.
Wait, they are older than you in other cities?
Oh, there's nobody. I mean, people, as soon as they become 55 or 60, they give up everything, start sitting in an easy chair, watching TV and all those. Nah,
True.
Classic grandfather.
no. Play soccer, man. Yeah, so that's good. My Saturday morning. And good. Then I can, yeah.
Sir,
Okay.
in which university do you teach?
Oh, I used to teach in a university, in a college
Oh.
in South Carolina.
Oh.
And then I found that the students were not that good. So after 8 years, I was the head of the department there. I quit and founded these camps where I can meet good students.
so, sir, you founded 5 camps, right? What are the 5 of them?
Not really founded. I didn't found really the Indian camp. The Epsilon India is actually the work of Vinay and Chintu. I was
Okay,
their
sir.
encourager.
Oh,
But I did found one in China, and it's going very strong.
China?
China?
which
Yeah,
camp?
Sir,
There
did
is-
you
there
meet
is
a
a-
coronavirus person?
there is a math path in China, very strong.
Oh,
Wow.
Yes. Oh yes.
But
And
did you find a student who had corona in China?
it is about 5 years old, and I go there every year, and I give speeches to a lot of Chinese people assembled, and I tell them that we Indians, we really love you. It's too bad we are neighbors, and it is natural that we will fight. But we still care about you. We are the Gandhi people, aren't we?
Yes, sir.
We have to fight because you are next door. But don't let that think that we are bad people. We
The
love
police
the
people
Chinese
arrested you?
people. I have told them.
But the
We
and
love
the
the
police
Chinese
people arrested
people.
you.
We
sir,
are-
I think the 4th law of thought is always fight with your neighbors, whether you like them or not.
Perhaps
we
that
don't
is
hate the
true.
Chinese people. We just don't want them to come and get our land. That's all.
Yeah.
Stay on your side. Don't.
All right.
Anyway, I
I
have
think
always
it's
told them,
yeah.
we are neighbors. We belong to the 2 ancient civilizations. We should work together. These difficulties we have are temporary, and all these things. And they love me there. because that's what I believe. But I still tell them we will fight because we are neighbors.
Sir, won't you get arrested if you say that stuff?
Pardon?
That's
We
what I
cannot
asked.
get yeah, Johan and
I think it's quite late for Dr. P now, so
Oh,
we will
okay.
you know why I kept talking?